Alright folks, it's the Poisson distribution for today, named after a French dude that did a whole bunch of stuff in stats. But for our purposes, we only care about his work as it relates to probability distributions. So here's a quick rundown. Firstly, we know it's a discrete distribution, meaning there's only a discrete set of values that this distribution can take. But what does this distribution actually describe? Well, it describes the number of events occurring in a fixed time interval, or region of opportunity. So the classic example is, how many customers does a bank teller get every hour? So in that instance, there's a fixed time interval of 1 hour, and this distribution might describe the number of events that occurs within that hour. But I'm not too sure that that many people are going to bank tellers these days. Perhaps a better modern day equivalent might be the people arriving at an Apple Genius bar because their freaking iPhone 7 headphones don't work. Back on topic. The next feature about the distribution is that it requires only one parameter, which is the expected number of events per time interval, lambda. So in this case, I've put a distribution here with lambda equaling 3, so maybe that's 3 customers every hour or whatever. But the other thing to note is that it's bounded by 0 and infinity. So unlike the binomial distribution, if you've been watching this series, the Poisson actually continues on forever. My graph here stops at 10, but there's theoretically a very small probability of there being 10 events in this time interval. And there's also a smaller probability of there being 11 and 12 and 13, etc. It's just I haven't included them on the graph because they become negligible. Nonetheless, it's a theoretical difference between this and the binomial distribution which needs to be appreciated. Now, what are the assumptions underlying the Poisson distribution? Firstly, the rate at which events occur must be constant. Another way of saying this is that the probability of an event occurring in a certain time interval should be exactly the same for every other time interval of that same length. The other assumption is that the occurrence of one event does not affect the occurrence of a subsequent event, i.e. the events are independent. So it shouldn't matter if an event just happened, that shouldn't influence the time interval till the next event. Now, these assumptions won't necessarily hold in reality, so it's often good to appreciate when you're using the Poisson distribution just how relevant it is to the question at hand. And we'll see with some examples here whether these assumptions are going to break down. So the next thing we can learn about the Poisson distribution is the PMF, or the probability mass function. Now, all that means is the height of each of these discrete outcomes, or the probability of getting each of these discrete outcomes when the mean is 3 in this case. So for example, if I wanted to find the probability of getting, say, 5 events happening in this time interval, I can use the formula subbing in the value 5 for x and subbing in the value 3 for lambda, because don't forget 3 is still our mean or expected number of events per this time period. So I can actually do this by hand, and in that case I'd get 0.101. But of course it is possible to use the wonders of Excel to do exactly the same thing. So if you use the Poisson.dist function, now these are the new statistical functions that were introduced to Excel in, I think, the 2013 version, but they're all standardized now, which makes things really easy. You might find other sources giving you the old formula here, and that'll work too, but I think it's good to start using these .dist functions because you'll see they're all exactly the same once you get the handle on them. So Poisson.dist requires 3 different arguments, the first of which is the value we're seeking, the number of events for which we're seeking the probability. So if we want 5 in that case, we'll put 5 as our first argument. The second argument requires the mean for the Poisson distribution, in this case that's 3. And the third argument requires you to tell it whether you want the cumulative distribution, which is called the CDF, or whether you want the probability mass function, the PMF. And of course we want the latter. So to write false, that tells it that we don't want the cumulative distribution. We want the PMF. So it'll give us 0.101 as well. So there's a 10% chance, roughly, 10.1% chance of getting 5 events occurring in this time interval. All right, So let's talk about the CDF now, the cumulative distribution function. Now that's not the height of a certain individual discrete outcome. That is the cumulative distribution, so all of the heights put together up until that point. And there is a formula for that involving a gamma distribution and all this stuff, which, look, you're not going to really need to know unless you're doing higher order statistical stuff. But for this purpose, we can use Poisson.dist again, but make sure we write true as that third argument. And in that case, it's going to sum up for us all of these bars up to and including the outcome where there are 5 events. So it'll sum up all of those 5 and we get 0.916. The other unique thing about the Poisson distribution is that its expected value, which we kind of need to be told, is actually equal to its variance. So lambda is also the variance of the distribution. So here we've got a mean of 3, and we'd also have a standard deviation of the square root of 3. Okay, remembering that the standard deviation is the square root of the variance. And what I've done now is just provided for you a couple of Poisson distributions for differing values of lambda, just so you get a sense of what they look like. So this is a Poisson distribution with lambda, that's the expected value, being 1. And this one is for where lambda is 2. Here's lambda being 3 and 4 and 5. Now, of course, in each of these circumstances, the distribution continues beyond 10, but I've just left the scale constant so you can kind of get a sense of how these flow from 1, 2, 3, 4, and 5. But be aware too that the mean lambda doesn't need to be an integer value. You can also have a Poisson distribution with a mean of 3.61, for example, or even a mean of 0.5. So there's no requirement for that lambda to be a full whole number. All right, so it's time for you to do a question. Let's give this a read. Exclusive Vines import Argentinian wine into Australia, and they've begun advertising on Facebook to direct traffic to their website where customers can order wine online. The number of click-through sales from the ad is Poisson distributed with a mean of 12 click-through sales per day. Okay, so we've got a mean of 12. That will be our lambda value. Now I've got 3 questions for you, and I'm hoping that you can pause the video here and give these a go and then see if we get the same answer. But we're after the probability of getting exactly 10 click-through sales in the first day, at least 10 click-through sales in the first day, and then more than 1 sale in the first hour. So see how you go with those. And I'm also going to give you a bonus question. Do you think the Poisson distribution is actually appropriate for this scenario in reality? So hopefully you can think about those assumptions and figure out whether they would hold in this case. So here's the answer to part A. The probability of 10 click-through sales in the first day is equivalent to the height of this bar here. Now this is a Poisson distribution where the mean is 12, lambda is 12. Of course, it goes a little beyond in this direction down to 0, and on this direction it goes up to infinity. But how do we find the probability of that bar? We can use the formula for the PMF and just sub in those values, for 12 being lambda and 10 being x, and we get a value of 0.105, which would be the same result if you used equals Poisson.dist and subbed in 10, 12, and false. So there's a 10.5% chance of getting 10 click-through sales in that first day. So there's the probability illustrated on the plot. All right, part B. What's the probability of at least 10 click-through sales on the first day? So how do we find the probability of x being greater than or equal to 10? Now that's equivalent to this whole yellow area over here if we sum up all of those together, going from 10 up until infinity. Well, unfortunately in Excel there's no way of finding the probability of getting a value or higher. So we're going to have to use the CDF, which is the probability of getting a value or lower, and subtracting it from 1. Now here's the trick. We're actually going to go 1 minus Poisson dist. 9 is the value of interest we're going to use here, because if you think about it, here are those green bars. We're going to go 1 minus the probability of all of these green bars put together. which is 9 and below. So you have to use your brain a little bit with some of this stuff. Knowing that it said at least 10 click-through sales, we know we were after 10 and above, which is 1 minus the probability of 9 and below. But putting in the appropriate formula here, we can get 0.758. And hopefully you got that exact answer. What about the probability that we have more than one click-through sale in the first hour? Well, this is where the properties of a Poisson distribution show themselves. If we know there's an average of 12 click-through sales in the first day, if it's truly a Poisson distribution, the mean number of sales per hour will be 0.5 because all we do is just divide by the total number of hours. So this becomes our new value of lambda. So this is the distribution now where we've got a lambda value of 0.5. So most of the distribution is going to be down here at 0 and 1 because we're only expecting 0.5 sales per hour. So we're most likely to get 0 sales in a given hour. Potentially we can get 1, and then it becomes less likely to get 2, 3, and very unlikely to get 4, 5, and 6 and beyond. So really we're after this shaded yellow region, which will include all of those values from 2 and beyond. To get that, it's going to be very much like the last example. We're going to go 1 minus Poisson dist, where we're taking the cumulative distribution, so putting true in that third argument, but we're doing it from 1, where the mean is 0.5. So we're going to be subtracting from 1 these two bars here, which is 0.090. So there's only a 9% probability of getting more than one click-through sale in the first hour. And I'll just reiterate that it's very important to read strictly what was written in the question here because it says more than one click-through sale. If it said 1 or more, we'd actually get a different answer because we'd be after this probability as well. So this would also be yellow, where x is 1. All right, so how did you go? Hopefully you got those same answers. Question D, the bonus question, asks you to think about what a Poisson distribution kind of is and whether it's appropriate for this scenario in reality. Now, I'll return you to our assumption where it said that the rate at which events occur must be constant. So in other words, no interval can be more likely to have an event than any other interval of the same size. Now, if you're dealing with clicks on Facebook over the course of a day, it's very unlikely for it to be a constant rate. How many people do you think are going to be clicking on ads for wine at about 2 a.m. in the morning? Well, actually, that's probably quite a few. How many people are going to be looking at it at, say, 6 a.m. in the morning might be a better question. Not very many, right? So irrespective of when in the day people would be likely to click on this, you get the sense that people's usage of Facebook would differ throughout the hours of the day, and also their likelihood to be attracted by an ad for wine. So in reality, it would not really be a Poisson distribution. But nonetheless, it is often good to use these types of distributions as it can still give us a decent picture of what's going on. Feel free to click through to the next video in the series where I deal with the hypergeometric distribution. And any poker players might be interested in that one. That is the classic poker hand distribution. But yep, I'll just leave these up here. And if you want to keep in touch, you can do so through these links.